Now you should be fine.
Thank you.
Thank you.
Can you see this?
Yes, we can see.
Great.
So next speaker is Costis. He's talking about towards solving CFTs with reinforcement learning. So Costis, please.
Okay, thank you, Paula. Thank you very much for the invitation to speak here. It's my first time in string data. And I'm going to be talking about some work that appeared recently towards the end of the summer in two papers, a long and a short version, in collaboration with Vasilis Niakos from the University of Crete and Georgiy Kantor, who's my wonderful PhD student who did most of the machine learning implementation. And I should say that this is very much exploratory research in this direction of trying to use reinforcement learning tools very much from the end user point of view towards coming with a numerical program for solving CFTs. So to most of you, the motivation here should be quite obvious. Conformal field theories are ubiquitous in theoretical physics. They govern the UV and IR behavior of quantum field theories. They appear in phase transitions and even in quantum gravity via the AD-CFT correspondence. But I think it's fair to say that the non-perturbative solution of these theories is actually hard. This is where interesting and innovative approaches, such as the modern incarnation of the conformal bootstrap, come along. And in this way of approaching CFTs, one makes certain assumptions about the spectrum of the theory, and then you check for consistency of these assumptions with the crossing equations, which I will introduce in a minute. These kinds of considerations are significantly assisted by powerful numerical schemes, such as which make use of linear and semi-definite programming methods, and in that way one can get sharp bounds in the parameter space of CFT data. What I want to talk about here is a complementary approach. It's a numerical approach, which is a little bit more in line with the original conformal bootstrap idea, where instead of using the crossing equations to kind of exclude regions of parameter space, we're trying to approximately solve the crossing equations. And it uses certain reinforcement learning techniques, which even for people such as me who are not very familiar with all this technology, you can just use it as a black box and get interesting results. So a couple of words about the theoretical framework. Consider a conformal field theory in d dimensions, and for simplicity, let's think only of scalar operators. So the spectrum of the theory is split into conformal primaries and descendants. Let's take a conformal primary scalar operator OI with conformal scaling dimension delta I. And it is known that the behavior of two such operators OI, OJ, inserted at points x1 and x2, when these points are brought very close together, is governed by the so-called operator product expansion, or OP for short. So you can see that the behavior of these two operators is written in terms of independent individual contributions of all the possible primary fields in your theory. And here, very importantly, a collection of constant appears known as the OP coefficients C, I, J, K. So it is a powerful statement in conformal field theory that you can calculate everything that you want in conformal field theory, all higher endpoint correlation functions in your theory, if you know all of these OP coefficients and the conformal scaling dimensions. And the idea is that the 2-point functions of conformal primaries set the normalization of these 2-point functions. Then you have the 3-point functions, which are very closely related to these OP coefficients, and then higher point functions can reduce 2- and 3-point functions using the OPE. So a first non-trivial example of that type is, let's say, a 4-point correlator of operators O1, 2, 3, and 4. And you can use the OP to reduce this to a lower point function by taking the OP between the O1 and O2 and 3 and 4. Sometimes this is referred to as the S channel. Or equivalently, by doing the OP between the first and fourth operator and second and third. This is sometimes referred to as the T channel. The fact that both of these approaches should lead to the same result, or more formally, the associativity of the OPE, leads to the so-called crossing equations, and these in turn lead to constraints on the CFT data. So for concreteness, I will focus on 2-dimensional CFTs. In 2 dimensions, the conformal algebra is part of a larger Virasoro symmetry, but nothing of what I'm going to be discussing here and what we do in the paper relies on that Virasoro symmetry. We only use the global structure and the global part of this symmetry. So the results can readily be extended to CFTs in higher dimensions. So in these two-dimensional examples, generically, the crossing equation can be written in this slightly ugly form. Let me tell you a little bit about the main characters of this equation. So here's the contribution from the S channel. Here's the contribution from the T channel. These Gothic C's that you see over here, subscript S and T, are related to the OP coefficients, but they are related to the squares of these OP coefficients. So they're part of our unknowns. There's also Z's and Z bars, which are related to conformal cross ratios of the insertion points of these operators 1, 2, 3, and 4. And one also has H and H bars, which are left and right conformal weights, the sum of which gives you the conformal scaling dimension, the difference gives you the spin. So in principle, you have the OP coefficient squared as unknowns, the scaling dimensions, and the spin. But here I will think of applications where I a priori fix the spin. So my unknowns are going to be the conformal scaling dimensions and the OP coefficients squared. And these functions G that you see over here are the so-called 2D conformal blocks. They are theory independent and are given explicitly in terms of these products of 2f1 hypergeometric functions. So this is the main equation, the crossing equation that we will try to solve. As you might already be seeing, this is a doubly infinite equation because these sums here over the left and right conformal weights are unconstrained. They should run over all the quasi-primaries of your theory. And moreover, because this is a functional equation on this Z plane, complex Z plane, and there's an infinite number of constraints. So infinite number of unknowns and infinite numbers of constraints. So these equations are actually hard to solve exactly. So one needs to find some simplification to produce a numerically tractable system. And you can do this in two ways. First, to truncate the number of unknowns, and then to reduce the number of constraints that you have. This truncation can be done straightforwardly by cutting off the sum in these two places up to some arbitrarily introduced delta max. It's a maximum conformal scaling dimension that you want to consider. And of course, where you introduce this cutoff will have an effect of how good an approximation you have to your actual analytic solution. Moreover, we can reduce this single functional crossing equation. So E here stands for equation, the crossing equation, which is a function of the unknowns and these Z variables, to a discrete set of algebraic equations when you fix these points Z and Z bar. Again, this is something that people do in the numerical conformal bootstrap. Is not that radical. So by assuming that you have fixed your external operators, you now have a system with a finite number of equations, numbered or labeled by NZ, for a finite number of unknowns, n unknown. And what we would like to do is to try and evaluate these truncated and reduced crossing equations for the number of constraints being larger than the number of unknowns. So this obviously will reduce to an overconstrained system, and you don't expect to have an exact solution, but one can actually look for approximate numerical solutions that minimize the components of this vector here. And I should mention that this approach in the numerical bootstrap, this approach to one of these aspects of the numerical bootstrap was already considered by Lee in 2017. We ended up coming up with it independently and then discovering that this paper existed. I should make a comment here that the choice of Z sampling that we use in reducing the number of constraints to something manageable is quite important and is motivated by a couple of considerations. There are theory considerations. So depending on where you are on the Z plane, you can get faster convergence of the OP. So therefore, if you impose a certain truncation of your the conformal scaling dimensions of primaries that are exchanged in the OP expansion, you can get a better approximation to your analytic result. But we also have some numerical constraints because in our implementation, we use certain Python packages which have some trouble with accuracy if you go to particular regimes of this Z plane. But since essentially we have arrived at a problem, which is an optimization problem, it is especially well suited to the application of reinforcement learning tools. And here comes the bit where we use reinforcement learning algorithms. We, being completely new to this field, we decided to use an off-the-shelf RL algorithm, which has certain appealing features for the applications that I have in mind. We chose to work with a popular soft actor-critic algorithm introduced by these people. The properties that we thought are suitable for us are that it involves a stochastic actor, which aims to maximize both the reward and the entropy of the entropy. And what this means is that the actor tries to maximize the reward while acting as randomly as possible. And we hope that this allows you to explore the global structure of your search space. More importantly, this algorithm can handle continuous state and action spaces. So here are conformal scaling dimensions, and OP coefficient squared can take any real value. So we need this feature. And finally, it's purportedly model-free and stable when applied to several scenarios. So we thought, why not? Let's try it. The other thing that we needed to choose is how to pick our reward function. And we, again, picked the simplest thing we can think of. The reward function is related to the total violation of the reduced crossing equation. So in this case, it's the Euclidean norm of this vector of equations. And we made a couple of choices. Both of them work relatively well, but we could have done something more complicated where we assign particular weights, let's say, in front of each of the components of this vector. We haven't explored that significantly, or at least the things that we have tried haven't led to particularly better or worse the results. Okay, so what we do in the paper, I'm just going to give you just a taste here. We try to see if the algorithm that we came up with by sort of taking this soft actor critic idea works for our purposes. And we try to calibrate it on two-dimensional minimal models, such as the Ising model and the tricritical Ising model. Here, I'm just going to give you one result for you to get a flavor of what we do. The 2D Ising model has a spin operator, so you can think of the crossing equations arising from the 4-point function of this spin operator. And we chose 29 Z points. And here, there's a very radical truncation with only five operators and therefore 10 unknowns. There is one OP coefficient squared for each conformal scaling dimension. The way that we perform the search here, again, is just a sanity check. We knew the analytic results, of course, and we decided, because you see here the action space is continuous, you don't want to, if you open up your search space completely, it can take a very long time for the code to find a solution. So for this particular example, we fixed the search windows for the reinforcement learning run to be very close to the analytic conformal scaling dimensions, but we left the ones for the OP coefficient squared actually open. And then the algorithm finds a solution. And as you can see, the solution here stays close to the analytic values. In principle, it could have drifted off far away towards some other minimum, but it seems to be doing the job. And for the OP coefficient squared, again, things are relatively good. Of course, as you come to higher conformal scaling dimensions, the results numerically maybe are not as good as for the lower ones, but there maybe you expect that there is some competition with some operator that has conformal scaling dimension close to that you haven't yet included. Okay, so the next example that we tried to attack is to see how this code can be used to try and discover for you a particular conformal field theory given a number of assumptions. And here I put discovery in inverted commas because we actually know the theory that we want the code to discover, but as far as it is concerned, it doesn't know what it's doing. So the assumptions that we have are the following. We consider a theory with an exactly marginal coupling, some spinless operator VP with conformal scaling dimension which is continuous, p squared, and this p you can think of as a proxy for this exactly marginal coupling. We also assume that there is some U1 symmetry under which this operator is charged. Therefore, there is a charge conjugated VP bar. And then the crossing equations that we would like to approximately solve are the ones for this 4-point function, VP, VP, VP bar, VP bar. There are two channels that you have here. You can perform the OP between VP, VP and VP bar, VP bar. This is the S channel where the quasi-primaries appearing in the OP are charged under the U1. And there's also a T channel if you perform the OP between VP, VP bar and VP, VP bar. And then the operators that appear there are uncharged. We also, because we know what, roughly speaking, what we want to get, this is a free theory, so you know the analytic solution. We have used as input the spin partition i.e. what number of operators you expect at each spin up to a certain level. And with this information as input, we run the reinforcement learning algorithm up to a delta max of 5.5 with 49 Z points and some fixed external conformal scaling dimension, or otherwise a value for P. And this is what the algorithm produces for you. Now, let me make a comment about how we reach these results. Again, because of the continuous nature of the action space, we do not start with all these operators. There are 18 operators, I think, and 36 unknowns. We did not just start with the search windows completely open for all these operators. We started with a lower delta max to begin with, so a smaller number of operators. With wide search windows, the code finds a minimum. Then you freeze these search windows and you increase delta max to 3.5. There's some new operators that come in. Then you allow these to have wide search windows while the previous ones are kind of stable and fixed. The code finds a minimum. You open up all the windows so that the values are allowed to kind of readjust themselves if this is not the correct minimum. Then you freeze them all again and increase delta max and so on until you reach this result. I should say that all the calculations that we do are done with laptop computers. Nothing took us more than a couple of days, including sleeping time. But again, here the goal was not to go for accuracy. It's kind of proof of principle. So without showing you what the analytic results are yet, I just want to say that already the algorithm finds good data that allow you to identify this theory. There is an operator, a spinless, chargeless operator of scaling dimension 2, which goes hand in hand with the marginal deformation that the theory has. There is an operator of spin 1 chargeless again of scaling dimension 1, which is identified as the U1 current, and also the 2D stress tensor. So here I superimpose also the analytic results. This is indeed the C equals 1 compact free boson CFT. So these are the analytic results. The VP operators, the 4-point function of which I was considering, are the vertex operators with unit momentum and winding, and the parameter P is related to the radius of the circle in target space. And as you can see here, the code has done an excellent job identifying the conformal scaling dimensions. So the conformal scaling dimensions are pretty close to the analytic values. For the OP coefficient squared, things are okay. I mean, they're not that great, especially if you go higher up to conformal scaling dimension 5 and so on. Here you have 4 orders of magnitude. So the accuracy for the OP coefficient squared is not very good, but I will make a comment about that and the possible sources of error in the next slide. One thing to notice here maybe is that there are certain operators in the S channel which have odd spin, where the analytic OP coefficient square has to be exactly 0. So the code finds that relatively well. But then it also finds, even though these things are very close to 0, it finds the correct analytic scaling dimension, even though this C multiplies the conformal blocks where these conformal scaling dimensions appear. So somehow it being just a little bit off 0 allows it to actually lock onto the correct conformal scaling dimension for these odd spin operators. Okay, so the RL algorithm actually has succeeded. I mean, as far as it's concerned, it kind of increases the reward. And in fact, the numbers that I have shown you improve as we include operators of increasing capital delta. So as I told you, we start with delta max, which is around 2.5, then 3.5 and so on, and the numbers you organize. So what you see here is better than what you start with when you're around delta max equals 2.5. And the idea is that if you increase that significantly, then the approximation to the full analytic result would keep getting better and better. One has to keep in mind the various sources of error for the OP coefficient squared. So of course, there are analytic errors which have nothing to do with the RL implementation. From the truncation of the conformal block expansion, if you have a delta max which is very low, then you expect big errors and so on. Then there is the choice of Z sampling, which is important when we reduce the crossing symmetry constraints. And again, different choices for Z points on the Z plane can affect the convergence of the OPEs and can lead to kind of results which are closer or farther away from the analytic ones. And I also should emphasize that here we've been talking about a single run, and it it is possible that the code actually was lucky or unlucky and so on. So in order to avoid statistical errors, one has to perform multiple runs and see, roughly speaking, a range of results. And finally, the choice of the reward function, maybe from the machine learning side, is important. We went with a vanilla choice of relating it to the Euclidean norm of the vector of crossing equations for fixed set points. Maybe you could try something else. And I should also mention that we did not really play very much with hyperparameters of the soft actor critic algorithm. Just basically tuning a tiny bit, two of them led to results which were relatively stable. Okay, so this brings me to the end of the,
you have
the
5
talk.
minutes.
Thank you, Pavel. So what I talked about today is a new reinforcement learning approach to the conformal bootstrap. Our code has progressed compared to what we have in the paper in August, where there was a lot of manual input. So now it's actually fully automated. And it does use as input a spin partition and predicts CFT data for specific theories. We calibrated the code on two-dimensional minimal models. Here I showed you just one 4-point function for the 2D easing model, but we do more in the paper. And then we use it to detect, in inverted commas, the C=1 free compact boson CFT. We get very good results for the conformal scaling dimensions. The results for the OP coefficient squared can be improved if one is looking after precision. And this is the outlook. There's many things to do. This is there's lots of low-hanging fruit around to pick. One can definitely improve the efficiency of the RL algorithm by improving the implementation, having a better understanding of the errors that I discussed a couple of slides ago. Also, it would be useful to parallelize computations, so you can, I don't know, send multiple instances of the same search to multiple cores to get and take into account statistical errors. And maybe more importantly, want to see if the efficiency with which the code can run allows us to scale the search up to order 100 unknowns, which, for example, is something that the standard numerical conformal bootstrap finds quite hard. So what I mean by this is, of course, we can do it. The question is, how long would it take? Would it be something that is realistic? So the kind of slightly longer term prospects would be to try and use this as a tool for finding information about high dimensional CFTs by, for example, making systematic use of theory constraints such as unitarity, which we kind of partly used in our search, but I didn't emphasize, global symmetry, supersymmetry, and also to use multiple correlators, mixed correlators, and so on to probe high dimensional CFTs. And the ultimate goal would be to come up with an algorithm, maybe that uses kind of some hybrid between these reinforcement learning tools and some other more standard numerical approaches, where you can just press a button and then the algorithm kind of determines for you the full theory by gradually adding in operators. So the idea would be that you know, you have a sort of basic set of low-lying operators as far as the conformal scaling dimension goes, and then you say, you know, if I want to add another operator below this delta max at spin 0, 1, etc., it tells you whether this is like a good thing to do or a bad thing to do. Then you do it and initialize the search, and gradually you kind of build up the full set of CFT data for your theory. So this is all I had to say. Thank you very much for your attention. I'm happy to take questions.
Hello.
Hi.
So any questions? Thanks, Costis. Okay, so if there is no...
So there's quite a few questions, Pavel. Sorry,
okay.
People have their hands raised.
Okay.
Should I tell? I don't remember who had the first question. Maybe Sven first. I don't know.
Yeah.
Hey, yeah. Thanks for the talk. I would be interested to hear a bit more on efficiency of these methods, in particular in comparison to other approaches, like and where do you see this heading as well? Like especially like as you mentioned, there's a lot of work in the numerical conformal bootstrap. how do you see you perspectively going with this?
Yeah, so I think the numerical conformal bootstrap does something which is slightly different from what we do, because they kind of have exclusion regions for, let's say, certain regions of parameter space. And then you find, as you exclude regions of parameter space, particular sort of cusps where special theories sit. And there you can become very, very accurate in your predictions. So for example, for the 3D Gaussian model, you can calculate the critical exponents like to very, very good accuracy and so on. However, I think they find it harder to specify, to start with a theory and kind of attack that particular theory, which is something that we can do over here. And then this scaling argument that I mentioned at the very end, I think they can do. I mean, I'm not an expert in the conformal bootstrap and the latest in the numerical approaches, but my understanding is that it is not very easy for them to do like order 100 parameter searches. They can do sort of, you know, small numbers of searches, whereas hopefully this one can go much farther.
Thanks.
Okay, Miranda, do you have a question?
Yeah, so very interesting work and very nice talk. Thank you very much. And I have a few related questions. The first one is, can you share some insights, maybe why you think like this is basically a search problem, right? So why reinforcement learning particularly, and why not other when compared to other search algorithms?
Yeah, so to be honest, we have not carried out a very explicit sort of comparison between standard searches. So standard, I don't know, gradient descent probably has a higher probability of getting stuck in local minima. What we like about the soft actor critic algorithm is that it allows you, because of this entropy maximization objective, it allows you to search the global structure of search space. And also, to my knowledge, reinforcement learning is very good just at optimization. So, I mean, I know that even with standard numerical approaches, you can introduce sort of, you know, stochastic terms and so on. So I'm not an expert in this area either. So I can't give you a definitive answer that we've looked at this and we've looked at something else and this outperforms it. But it looked like a cool and interesting sort of direction to take.
Yeah, thanks. That works, and that helps. And a second question is about this upper bound of the scaling dimensions. I mean, so for instance, you started with 2.5 and 3. I mean, what told you? I mean, of course, in this case, we know the theory, but without knowing first the theory, how do you know?
Yeah, I think a way to think about it is that you know, you want to start with a set of operators that you know that the theory should have, let's say like a stress tensor and so on, and also with a small search that you perform without putting sort of, you know, very strict bounds on your search space. And there the algorithm can work relatively fast and sort of lock these values in, and then you can introduce one by one the additional operators, or at least that's kind of the long-term strategy that we have in mind.
Yeah, but am I right that we're assuming that the higher scaling dimension operators do not like?
Oh yeah, good. So that's a very good point. So there are some theorems, I think, by Richkoff that the OP converges quite rapidly. So the hope is that, you know, indeed you don't get results that are very, very far away from what you expect. The choice of Z points that I mentioned at some point is quite important, because, you know, depending on where you're on that Z plane of conformal cross ratios, the OP can converge faster or slower. So these kind of two aspects are interrelated, but in some sense, if you go to order 100 unknowns, I think, you know, you should get a very good approximation, and that's why we want to go towards that direction.
Right. So a final question, also a technical question, is that you mentioned that it was a couple of days for you on a small computer. So I mean, do you already see like where the bottleneck is gonna be, or?
Yeah. So there's many questions, but kind of. Some of the implementation kind of gets stuck with the calculation Papageorgakis 2F1s, which appear in the conformal blocks. And there are different Python implementation packages. One of them, which is SciPy, I don't know if people have worked with these things, which are very, very fast, but very unreliable around particular sort of regions in the Z plane. NP math is very good, but it's very slow. So one has to kind of be a little bit, this is like the first bottleneck that we found. And by changing one for the other, we found an improvement, let's say, of 20 orders of magnitude in performance. But you have to be careful of well, we can discuss that a little bit more later, maybe.
Right. So, I mean, and also, like, do you have any idea of like how the scaling of the time.
Not yet. So this is something that we're actually looking into now. To go to order 50
Yeah.
unknowns is something that we're planning to do in the next, I would say, month. That would be a good indication of this, whether what I've told you here is realistic or not.
Great, thank you very much.
Thank you, Miranda.
Okay, Tanya, do you have a question?
Yes. Hi. Thanks for the nice talk. Do you think this method of solving bootstrap using RL algorithm, will that work to solve bootstrap equation for boundary CFT, or like any interacting CFT that uses this epsilon expansion?
Yeah, I don't think there's going to be anything that prevents this model from working in that case as well. You just have there, you know, more, let's say, OP coefficients to think about, because you can have sort of interactions between the boundary and the bulk operators and so on. If you take all that into account, you should be able to apply what I'm talking about here as well.
Okay, and another thing is like, could you once more clarify that how to take this precisely take these J points?
Take which points? The Z points?
Yes, exactly.
Yeah, so the Z points, again, the theoretical considerations and numerical considerations. This implementation, for example, of SciPy is one that kind of restricts us within a certain region. And I should say that the choice of Z points is something that in the standard conformal bootstrap, the numerical bootstrap people are discussing. They expand around, they tailor expand conformal blocks on particular Z points. It is a bit of an art. I don't think anyone really knows what is better. So we use some sampling that works in the standard conformal bootstrap, but I can't give you a very definitive answer.
Okay. Thanks.
Okay, I don't think there is any more questions. So let us just all thank Costis for the wonderful talk. And thank you, Costis.
Thank you.
And the next week